star that allows us to do verification, writing crypto protocols, proving things about them and stuff, is this feature called refinement types. Okay, it doesn't really exist in most mainstream languages. It's a form of dependent types, if you know what those are. But essentially what it means is that we can give expressions types not just like int, bool, array, and so on, but you can say that an expression has a type x:t, which is over here, and in the parentheses we have c, where c is a formula. We can say that c is an invariant that must hold about x. So x has a type t, and x must satisfy the property c. Okay, and c can specifically refer to the thank you for the or the other way around. I don't know what I want actually. So all right, I'll make do. Okay. Oh, that is working there. Oh, I have a beautiful green dot. Okay. So the values of this type are values of type t such that the condition holds. So for example, I can write something like this, which is that there is a type of natural numbers called nat, which consists of all the integers such that this property holds, that 0 is less than or equal to n. So it's a very simple definition of natural numbers. It's just a way for me to define a logical invariant or logical precondition, postcondition, these kinds of things on the values I want to manipulate. And this is kind of enough for you to specify a lot of things about your programs. And then be able to verify them just by type checking. So we are going to just use type checking to verify it. You can also sort of decorate your functions and say, for example, I have a function called read, where I say, okay, I want to read n bytes from the network, say, and what read is going to give me back is a sequence of bytes where the length is less than or equal to n. This is how typically network protocols work. You say, please give me n bytes. It may not actually give you n bytes. It will give you some number of bytes which is less than or equal to n. And this is important because you might have already allocated a buffer of n bytes, and so you don't want more than n, but you're okay with getting less than or equal to n bytes from this function. So this here is a post condition on this function. So this function has a post condition that says whatever output it gives me has this property. That there is an invariant on that type, that all things of type nat have to be between 0, has to be greater than or equal to 0. Okay? So these are called refinement types. The other kind of type you're going to use is something that is actually common in many programming languages, including Java and OCaml and all of these things. It's called abstract types. And the combination of abstract types and refinement types is going to allow us to specify all the properties you want. In particular, suppose I have an encryption module, and it's called AES, for example, right? So what I'm going to say is that I have a type here called key. And I'm not telling you what the type key is. I'm just saying there is some type of keys. What this implicitly means is that elements of this type key are opaque. You cannot do anything with them except for the functions that come down below. These are the only ways you can manipulate things of type key. Okay? And so this abstract type key is a way for me to specify a secrecy property about elements of that type. So here I'm saying there's a type key, which is completely abstract. You don't get to know anything about the type key except the functions I'll give you below. I have a type called block, which is not abstract. A block is a number of bytes where the length is equal to 16 for AES. It's going to be 16. For other ciphers, it might be something else. I have an encrypt function and a decrypt function. Okay, I might also have a key generation function, but here only encrypt and decrypt, where you give me a key and a block, and I'm going to give you back a block. So there's actually just a block encrypt function here. Of course, we can define an arbitrary sized encryption function for which I would need to provide a cipher block, well, a mode of operations. I might have to say it's an AES CTR or AES CBC or whatever it is. So in this case, I'm saying that the encryption is a function that takes a key, a block, and gives me a cipher. And there is a property, a post condition, that the value that I'm giving you out here has to be the AES, the value of the AES function applied to KNP, where I'm assuming that somewhere else in the world I have defined formally what AES means, which is going to be exactly the algorithm of AES. Okay? So for AES, this is less important because really, what is the difference between an algorithm and an implementation? Not much. You know, it's the same thing. But for things like bignum-based things like elliptic curves, I might want to say that the scalar multiplication is giving me the actual elliptic curve scalar multiplication value here. If you do the math, the result is going to be exactly the one that I'm getting out of it. Okay, so these are the kinds of post conditions you can specify, and also preconditions. So here there are implicit preconditions for encrypt, and the precondition is that you must give me a key and a block, which means that this one has to be of that type, and the block has to be some bytes of size 16, and the post condition is this, right? And what a star is going to do for us is that it's going to type check the code, which means it's going to prove that all the code satisfies their declared types. And there is a theorem that says that if F star actually proves type check some code, then that code is safe, for some definition of safe. In particular, it means that in all runs of the program, no matter how many times, so let's go back here, no matter how many times you run the program, with what applications, with what libraries, you will never find a type error in the resulting code, which means that any time you reach a piece of code where something says I am of type NAT, you are guaranteed it will be greater than or equal to 0 in all runs of the protocol. So it's a static type checking of this code, of the code that uses these interfaces. The code that implements these interfaces is going to guarantee that in all traces of the program, that property holds. And this is called safety, which means that whenever a program is type checked, it's safe, which means that at runtime you will never have a type error. And since types, in our sense, are actually invariants of the program, we are saying that in all runs of the protocol, those invariants are being satisfied. And if you can code up your security property that you want in terms of these kinds of types, you're getting the guarantee that in all runs of the protocol, the security guarantees, such as the secrecy of your keys, the authentication of your sessions, is guaranteed just by typing in F star. And the way F star itself works is that you have to provide it a module. In this case, suppose you're verifying some module called RPC. We give it the F star code for the module. We give it the F star interface for the module. We give it some libraries that you might want to use for this. For example, some authenticated encryption library maybe. And F star will take all of them, type check it by calling Z3, the SMT solver, for all kinds of simple things that you have to prove. And once it can prove all the invariants, it will say, okay, you're done. And now you can compile it to OCaml or C or WebAssembly or whatever it is that you want. And I'll show you one example at least on the screen of how it works. But let's sort of go a little bit deeper before I go to the demo, which is what kind of properties can you prove here, right? So if any of you have programmed in C, and many of you who have actually implemented your crypto primitives or protocols probably have done that in C, you know that a big problem in C is going to be that you can have segmentation faults, you can have buffer overruns, underruns, and so on. So what you need to prove is memory safety, right? So in F star code as well, you can define arrays and sequences, and you can write and read from sequences, and you can write outside their bounds and so on. But you can prove that your code is memory safe. And this is how you prove it. So suppose there was a function called fsum, which is going to add two big nums together. So the two inputs to it are A and B, which are both field elements, FLMs. So you provide two field elements, which are both big nums, and you're going to add them together. So this function declaration says that fsum is guaranteed to have the following properties. First of all, it's a stack function. A stack function means it does not allocate on the heap. It does not put new things into the heap. All it does is allocates on the stack and deallocates from the stack when it gets out. This is true for a lot of crypto code and a lot of crypto protocol code, that you do not want to touch the heap. You only want to do everything on the stack. So that's the first thing you see, the stack unit. And then it has a precondition marked by requires and a postcondition marked by ensures. The precondition says that in the initial heap H, okay, in the initial memory that you're given, the pointer A and the pointer B must both be live, which means that they cannot be null. They have to be validly allocated blocks of memory. And they have to be disjoint. So fsum requires them to be disjoint, which means they cannot overlap in any way. They have to be different parts of the memory. And if you add A and B together, they will not overflow. What that means is that there is enough room in A and B that if you add them together, there will never be any integer overflow. And you have to prove this statically. Okay? So which means that if you're given two A and B and you try to add them, and they're both arbitrary 64-bit integers, for example, you cannot prove that because 64 plus 64 might actually overflow. But if you know that both of these numbers have less than 63 bits, for example, less than or equal to 63 bits each, and you add them, then they're not going to overflow. So now you will be able to prove that precondition. The post condition is that in the final heap, H1, in the final state of the function, A1, A and B are still live, which means you did not deallocate them or something. They are still live. You did not free these pointers. You promise that this function only modifies 1 means only modifies A. It doesn't modify B. It only modifies A. It doesn't modify anything else in the world except for A. And the final value of A in the heap H1, if you look at the value in A, is in fact the sum of the two values A and B in the initial heap. And eval is a function which is in this particular case going to take, it's not a built-in function, it's something we have defined, which will take this FLM and will give me the actual integer value out of it. And it's saying the integer value of A at the end is equal to the integer value of A plus the integer value of B. So that's the specification of fsum, which is the sum of two field elements, which in this case we use for a lot of things. It's ensuring this type, it's ensuring that all the pointers that you use are live, all the array accesses are within bounds, the memory areas that you want need to be disjoint are disjoint, and it tracks all the more things that you modify. Okay, and all of your functions have to be annotated like this.
What is the meaning of the H in the beginning before every element? The H.
The H?
Yeah.
H0,
So, H0, H1, and H are the heap. So the initial memory, the final memory. So this function is going to change the memory, right? So in the initial memory, there must be, which is H. Well, I could have called it H0 in the requires, but H0 is the initial memory of the function, H1 the final memory of the function. The precondition gets to talk only about the initial memory. The post condition can talk about the relationship between the initial and the final memory.
But it is not really the heap, it is the stack in our case.
No, A and B can be on the heap. A and B are usually on the heap. What we are saying is that this function does not allocate anything on the heap. Okay, it's not allowed to put things on the heap. It can read pointers from the heap as long as, and modify them even, but it's not allowed to add new things to the heap. It's not allowed to do any mallocs or freeze actually.
Is it allowed to allocate on the stack?
Yes. So it can allocate on the stack, and as soon as you come out of the function, it will go away. So we don't have to say much about that. Okay. And of course, you just to clarify, this kind of a function is a stack function, but you can also have heap functions which are allocating on the heap, which are freeing from the heap, and do lots of manipulations. But for them, you have to prove even more things, because often a lot of the verification effort is actually in tracking the pointers in your program. Okay, if you're just on the stack, you have less work to do. There was a question. Okay. All right. So that's just for proving memory safety. Okay, and this is the kind of thing that you end up writing all over the code that is doing pointer arithmetic, your array accesses, and so on, and manipulations. If your code is only reading from memory but never writing to memory, the proofs become much simpler. You can actually allow many of these are boilerplate things that you don't even have to write. But this kind of function is actually reading and writing to memory, and you have to very clearly state what it is touching and what it isn't. A typical example is I might be calling this function, and when I call this function, I have 5 arrays in my state. I have A, B, C, D, and E, and I call the function on A and B. After I come back from the function, I still want to use C, D, and E. How do I know that C, D, and E have not been modified by fsum? I don't, because really in C, these could be global arrays. They could have been modified. So this actually guarantees to me that the only thing that was modified was A, B wasn't modified, and any other array I did not give you, and which is disjoint from these two arrays, has not been touched. And that's very important for me to continue verifying my code. These are called frame conditions, actually. I just realized I may not have started recording, so let me quickly do that before I get in trouble. Okay. So here's a second, probably more interesting one for us, which is secret independence, right? So what we want in a lot of crypto code is what people call constant time coding or side channel resistance. But both of those terms are far too broad and weird for me. So I'm going to use a different term called secret independence. The idea is that you want to use the types to enforce what is called a constant time coding discipline. In particular, you don't want your code to ever branch on secrets, and you don't want to use secret indexes to look up arrays or look up memory. Okay?
And if you do those, if you follow those rules, those two rules, at least within the semantics of high-level languages like C, you know that you don't have any timing attacks at the C level. Now, this doesn't mean that the compiler is not going to introduce new timing attacks at the assembly level, and especially these days, there are lots of weird things happening at the hardware architecture level even that we can't really prevent. But at least at the C level, we know that there won't be any timing channels. And this is already pretty good. Okay. It also doesn't guarantee the absence of other kinds of channels, like power channels and so on. And for them, you need other kinds of guarantees, but this is the minimal guarantee that you want for side channel resistance from any code that you write. And we want to be able to enforce that by typing. So the way we do that is that in our program, all the secrets that we have, all the secret arrays, nonces, whatever, are going to be represented as arrays of what we call hidden integers or secret integers. And a secret integer is something like the one above, which is a hint64. It's a hidden integer. It's a uint64, really. But I'm making it an abstract type, which means you don't know what the underlying representation of hint64 is. It could be uint64. It probably is uint64, but you don't know. You don't get access to it in the program. All you can do is call functions on it. You can call plus, minus. You cannot call division because division is not constant time on most architectures. But you can call XOR and these kinds of operations on this secret hidden integers. Okay, you can extract out the underlying uint64 from this secret integer by calling the function v. But the function v is in a special mode. It's a ghost function, which means you can extract out the value only when you're doing proofs. You cannot use it in code. In code, you cannot use the actual value of it. You cannot print out the value of a hidden integer. You cannot convert it to an array index and look up something. You cannot compare to hidden integers. There's no equality on them. You can only you can convert a regular integer into a hidden integer, but you cannot convert it back. Okay? You cannot convert it to a Boolean either. So you're only allowed a very small curated set of operations that you are allowed to do on it. But then you can put them into buffers and make a secret which is basically an array of hidden integers. And that's typically how you represent your secrets. Okay? So for now, in this API, you would say no comparisons, no division, no modulo. But on some architectures, it might turn out that even multiplication for 64-bit integers is not constant time. And if it's not constant time, you can't allow it in there. Or you have to re-implement it in a way that might be constant time. So this is your ground truth about the machine model that you're working with. So for all your machine integers, you have to give me an exact specification of the operations that are safe to use. Okay? And a lot of people have already worked on this, so you can take for 32, 64, 128-bit integers and for vectorized instructions exactly what the spec that you want to use is, and then you can verify the rest of your code against this. But the rest of the code, which is all my crypto code, all my protocol code, will always use this interface, which means it can never accidentally reveal a secret. So if I have a secret key somewhere, I can look up the 10th byte of the secret key. Yes, I can do it. But once I have that 10th byte, I cannot do anything with it. I cannot print it out. I cannot compare it with another byte. I cannot put it on the network because it's not a concrete byte. It's a hidden byte. All I can do to it is plus, minus, XOR, but I still will never be able to get out the concrete value from it. And we can prove that just by enforcing these types, we get this particular notion of side channel resistance called secret independence, and we can get it at the C level for all code that is compiled from these ones. But the most interesting part of the proof, even if it is not the more exciting because it's not attacky, is actually proving functional correctness. Okay? How do we know that the algorithm that we are implementing is actually the algorithm that you want it to be implemented? So let's take an example, which is the poly 1305 message authentication code. It's a polynomial map, which means that you're given a key and you're given a key and an initial value m. What you're going to do is you're going to compute a polynomial like this: m plus w k1 plus blah, 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 plus wn to the power to multiply by k to the power n. You compute a polynomial on k using the message w1 to wn as the coefficients. And you do this, evaluate this polynomial modulo some prime. And in this case, it's called poly 1305 because you evaluate the polynomial modulo 2 to the 130 minus 5, which is a prime. So what you're doing here is this MAC computation is authenticating a data stream by encoding it as a polynomial in the prime field modulo 2 to the 130 minus 5, evaluating it at a particular point k, and then masking the result with n, which is the second part of the key. So the k and the n are together the key for this macking construction. So if you know of the GCM mode, which uses a MAC which is called G hash or GF128, it's a very similar construction, but there the additions and the multiplications are done in the Galois field of 2 to the 128 modulo irreducible polynomial. Here it is actually prime modulo computations that we're doing, but the construction is very similar. So if you actually are trying to implement this polynomial MAC, and I'll show you an implementation of it in a second, you're basically going to do arithmetic in this 130-bit modular field, prime field. So 130 bits is larger than any integer that is available on your machine right now, so you need big num arithmetic for it. It's a very small big nums, they're only 130-bit big nums, but you still need a specialized big num library. And every implementation of Poly 1305 that exists, whether it's in assembly, whether it's in C, each one of it has its own little big num library embedded into the implementation. And this is actually a common feature. If you have any elliptic curve in any library, you look inside it, there will be a big num library inside it. And that's because for side channel resistance and for efficient optimizations, they want to do big num or modular operations in their own way, for their own prime. So for example, for 64-bit machines, how do you represent a 130-bit number? You can say I can do 64 bits, 64-bit 2 bits, right? That's one way of doing it. Or you can say I'm going to do 44 bits, 44 bits, 42 bits. Now it turns out that 44, 44, 42 is efficient in on certain architectures, and so that's what a lot of implementations of Poly 13005 use. Okay? And then you want to do modular arithmetic with respect to this prime 2 to the 130 minus 5, and it turns out that there is a nice equation that if you do 2 to the 130 times a plus b modulo p, it's basically the same as 5a plus b modulo p, which means that if you're trying to take a big number, which is way more than 130 bits, and you want to reduce it with that prime, you truncate it at the 130th bit, you take all the values on the which are greater than the 130th bit, you multiply it by 5, and you add it back. And that's an easy way of computing the same value modulo p. And that's in fact the reason why that prime was chosen in that way. And there are many other primes like this which are chosen specifically to make modular reduction efficient. Alright, so if you want to look at the spec of Poly 1305, it's not so important. I'll show it to you on a bigger screen in a second. You can actually write it in about 40 lines of code. Okay, so the spec in F star is going to be really, really small, and it's going to be using natural numbers. It doesn't have to do anything with big nums. It just says, here's a spec, you're going to do this polynomial evaluation, blah. Okay, so that's the spec which is taken from the RFC is really small and compact. But then you have to implement it. So what you're going to do is you're going to implement this big num representation, which is 44 bits, 44 bits, 42 bits. We're going to factor out the generic big num operations like multiplication and addition into a shared library. We're going to optimize the prime specific operations for Poly 1305. And then we're going to allow incremental macking like many implementations need it. You want to keep adding more and more data as data arrives. And of course, we want to do all of this with secret independence. So all the keys that we are using in Poly 1305, and even the plain text, because we don't know, maybe the plain text is a secret as well. We're going to treat them all as secret, and so treat them all as arrays of secret integers. And we're only going to use a stack and no heap. Okay. So if you do use all these principles and you implement Poly 1305 in C, but actually we are implementing it in F star in a style very similar to C, you end up with a piece of code which is about, 1,500 lines of generic big num library, which can be shared between other things, plus about 3,000 lines just for Poly 1305. Okay, this includes the proof and everything. And if you compile it down to C, throwing away all the proofs which you would, then you end up with about 450 lines of C. So we had about 40 lines of spec, 450 lines of C, and to bridge between those two, we had to write this much code, which is about 4,500 lines of code. So it's a significant effort, but at the end of it, you get back a fairly efficient implementation, which has been verified for all the properties you care about.
So,
yeah.
There was some attack on implementations of Poly 1305. be injecting, you know about that?
So what is this?
I don't know, I know that there were some attacks on implementations of Policy 1305.
There have been like around 6 bugs in the last 2 years on various implementations. I don't know if they were ever exploited into a real world attack, but they were certainly bugs. And there have been bugs in OpenSSL, in all the implementations of Poly 1305, and also in GCN and so on. Exactly, these are very small pieces of code, but there's been bugs in them. Primarily because you have to do the arithmetic with the proper carries, and if you try to optimize it too much, you lose that. So one thing to remember is that a lot of people who write crypto code actually write it in assembly for speed. But assembly is even harder for you to get right, and often there is always potential for bugs. You might have a lot of speed, but there might be bugs. So we are writing all our code in this language called Lowstar, which is a subset of F-star that mimics C, which means that your memory model that you're going to use is very much like C. You're only going to use arrays and pointers in a very restricted way. All your code has to be first order, and you can use some combinators for loops. And you can use a few low-level libraries for arrays, structs, and C-based types, but you don't get to use all the fancy types that you have in F-star in your code. However, you do get to use all the fancy types you want and all the fancy higher-order polymorphic structures you want in your proofs. So you can build very complex and reusable proofs, but the proofs are talking about artifacts, the code, which is really first order and simple and C-like. Okay? So the motto of that language is that the code is low level, but the proof is higher order, high level proofs. Okay? So if you do more proofs in this language, you'll realize that you're actually proving things about C, but you're not really restricting yourself in your proofs. You can use all the fancy modern programming language features you want. And there's a compiler that takes code written in this Lowstar subset and compiles it to C through a series of transformations, each of which has been formalized, proved correct, and so on, so that if you have a proof of your F-star program, like the ones that we're talking about, like secret independence, functional correctness, memory safety, you can show that that goes all the way down to C code. Of course, not beyond C code. So if you want to go all the way down to assembly code, you have to use a verified C compiler, like CompCert. People typically don't because it's too slow, but you can use it and get the trusted chain going all the way down to assembly. All right, so before I show you code for on Emacs, just to give you a sense, well, I don't think you can actually read this. The lights are too bright, I guess. Maybe I skip it. Well, the idea was basically to show that on the left-hand side, you have a kind of fairly large program in Lowstar code, but it includes a bunch of invariants for memory safety, a mathematical spec of Poly 1305, the code that is actually going to be executed, a bunch of lemmas and annotations that you have to put in there to prove that this code is correct. But then you compile it, you throw away all the proofs, all the annotations, and you get back something which is very compact, which in C. Okay, so what we have done in Hacklestar is, okay, let's now go to this. Let's see what it feels like to verify this kind of code in, maybe I have to escape. All right, so this is the spec for Poly 1305 in my Emacs buffer. This is an F-star. So here's the spec for it. Okay. So I can say that let this be the prime. So the prime is going to be 2 to the power 130 minus 5. I have a type of elements in this field, which are all natural numbers greater than or equal to 0 and less than the prime. I can define two operations here, the field addition and the field multiplication operation. And I'm specifying that they take two elements and they will return me an element. So let me say that is going to return to me an element. And I can say that there is field multiplication, which is going to return to me an element. And what is field multiplication in this prime order group? Addition is just E1 plus E2 modulo prime, and multiplication is E1 multiplied by E2 modulo prime. Okay? And 0 and 1 are both elements, and they are 0 and 1. Okay? So I can verify this code, and blue means that F-star says it's verified. It says that yes, 0 is an element, yes, 1 is an element, fadd and fmul do return elements. Now what could go wrong? So suppose I made a mistake in fadd,
And this is just a spec. I'm just giving you an example. And I added a 1 to it. Okay, so now the FAD is going to return to me some value which could be as high as a prime. And immediately F star will find an error if I try to verify it. And it's going to say, sorry, I cannot prove it. And if you look at the details of what actually happened, it was trying to prove that the result of FAD is an LM, which means that the result of FAD has to be greater than or equal to 0 and less than the prime. And it couldn't prove it because this definition does not guarantee that. The result of FAD, if I add 1 here, could be as big as the prime. Similarly, FAD, which is E1 plus E2 modulo prime, if I subtract 1, it could go below 0. So if E1 and E2 are both 0, then E1 plus E2 modulo prime minus 1 is minus 1, which is not in the type. So I can already verify, even at the spec level, that I didn't screw things up by actually type checking that this is something in this. So okay, so what else can I ask? I can ask that FAD of 0 and 1 is 2. No, 1 and 1 is 2. And it'll say yes. If I try to prove that FAD of 1 and 1 is 1, it'll say no. So it's able to prove arithmetic things quite easily because it is using Z3, the SMT solver underneath it to prove these kinds of things. Okay? And a lot of what we do in code is arithmetic. It's pointer arithmetic, it's big number arithmetic, but it's all arithmetic. We can also prove symbolic properties, which are not about just one thing. You can ask, okay, x, y. Let's say that FAD of x and y is the same as FAD of y and x. And since it knows the properties of arithmetic, commutativity, associativity, and so on, this one is not going to work, but this one is work. It can show that FAD xy is FAD yx. And it can not only show that, it can actually use it in its proofs. So you can prove, so FAD xyz, let's see, associativity, FAD yz. So I'm trying to prove associativity of the field arithmetic, right? So FAD of FAD xy z. So this took a little bit longer because it had to kind of look up the right lemmas, apply them, and so on. But it's able to automatically prove properties like this, right? And these are the kinds of properties that you will need when you're trying to prove things about some complicated elliptic curve operation, which is based on a bunch of field operations, but then it's combining them together into some elliptic curve operation that you're trying to prove. So these are the kinds of things that that it knows about. Then we can define a block size, a block which is a number of byte sequence of block size, a key which has to have this size, so we are actually specifying the key in the block. Okay, now we can say what's the state of poly 1305. A poly 1305 is a polynomial MAC. It keeps at any time the two parts of the key, which are both elements, R and S, and an accumulator, which is the accumulator that it's keeping going. Okay. The set accumulator function is going to initialize or set the accumulator in the state. There's an update one function which is updating one block, and we can prove that it's correct. What it's doing is taking some value which is less than block size, a block of that size which is less than a block size, taking the state and updating the state. And then I can apply this multiple times in a loop. So this is a loop which says, I'm afraid this is not okay, that's better because the fonts are so big that it's difficult to kind of see what's happening, but okay. So here's update blocks, which is updating a sequence of blocks. It's saying repeat n times the following function. Every time for every I, you're going to slice the text, one block size of the text from block size times I to block size times I plus 1. So you're going to take one block of the text. You're going to call update on the state with that block, and then you're going to continue. And you're going to keep running it as many times as you need. And that's the operation that is update blocks, which is updating multiple blocks. So if you wanted to do encryption with counter mode or cipher block chaining, it's going to look very similar. You just take block by block and you just fold it in and you process it. And finally, the polynomial computation here, the polymac, is going to be, you take, apply the blocks to a whole bunch of blocks, and then apply a special kind of update to the last block over there. And here's you finish the computation, but this is how you compute the final MAC. Then there are some ugly things you have to do. In the spec, it says when you get your R, you have to clamp the first bit, the 17th bit, the 25th bit, and so on. And you can do that kind of thing here. Then you can initialize the poly 1305 using this, and you compute the MAC like this. Okay. So the whole, if you want to do it in the full gory detail of the spec, this is the full RFC spec of poly 1305. You can go line by line, and it's basically the whole spec that we have here. You can also write the spec in a different style, and then you can prove that the two specs are equal by just asking S star to prove that they are the same, and S star will ask you for some help, but then it will be able to prove that. Now, if I go to the actual code for poly 1305, that's going to be much uglier. Okay. Right. So here I have a notion. Let's see. So I'm going to be using, let's just fsum. No, let's go to the big num library. So if I just want to do fadd, which is fsum, what I basically end up having to do is to say that, okay, I have something called an flm, which is a buffer, a list, an array of uint64s, and another flm, which is an array of uint64s, and the two of them have to be disjoint, blah, 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 and a bunch of conditions. And then I'm going to, in place, map this addition function on every single array element. So I'm actually going to modify the array element by doing a equals a plus b. So it doesn't really look like C code, but really it's a equals a plus b, a0 equals a0 plus b0, a1 equals a1 plus b1, and so on. Okay, and here I have to do a proof that in fact if I evaluate this function, it is exactly the same as a specification of fadd, which is basically it's going to give me a result which is a plus b modulo p. And similar kind of thing I have to do for every single function that I'm doing, but now I'm working on arrays. I'm not working on integers anymore, and have to map the result of this computation to the result on integers. And that takes a lot more effort to prove. So this is where the thing blows up. So if you look at Hackle F product, you have like lots and lots of things that you have to prove. How do you carry things? How do you shift things? These are all lots and lots of things. You let's see, you do scalar multiplication, then you have to have lots of lemmas about carries, and so on. So in the end, to actually prove things which are mathematically relevant, you might have to do a lot of proof, but these are all proofs you have to do anyway by hand. This is just that this is a machine check proof that your algorithm for doing poly 1305 field arithmetic is actually correct. And then you get to, once you verify the code, you get to compile it down to C. And the C code, which is also released, looks reasonable. Let me look at fsum now. So for example, scalar multiplication basically looks like this, where it is a loop that is going from 0 to 3 because you only have 3 limbs, and it's going to just do output I equals input I multiplied by some scalar. Okay, this is uint 128 arithmetic, which is why it looks a little bit ugly, but it's really just scalar multiplication with a scalar and an array. So the resulting C code looks as compact as you can imagine, and reasonably good looking, which is compiled from F star, but the source F star code you're going to have to do lots of proofs on. Anyway, so this is the style in which we code all of this stuff. If you're interested, you can go to the Hacklestar library, which is on GitHub, and you will see that in the specs, we have a bunch of specs which are written in many implementations as well, including AES, Cha-Cha, various curves, including ED25519, Crypto5519, and so on. We have Galois field arithmetic there, modern things like Gimli and Ketchak, and even I have a spec of Kyber in there, and we're doing more things like post-quantum key gems and so on that you can write in this style, and you can write verified implementations of them. Okay, so back to more or less wrap up. So we have verified a bunch of this code. Verification takes quite a long time. I mean, both in manual effort to actually build the proofs and then actually to run the proofs. And it shouldn't take so long because many of these properties we are proving are very simple. So we are actively trying to make it easier and faster. And I think we are succeeding. But we have students who can come and actually do new proofs and new primitives fairly quickly. So if you have a new crypto construction, you want to build a verified implementation or a high assurance implementation of it, I think it is well within reach right now to do it in a tool like F-star, but there are other tools like that too. There's one called VST, there's one called Fiat, and so on. If you want, I can kind of tell you about the right tool for whatever primitive you want to implement. Okay. The nice thing, and this is probably important for people who are submitting things to competitions and so on, is that the resulting code's performance is pretty darn good. So the code that we generate from HackleStar is faster than OpenSSL, C code. It's faster than libsodium, faster than things people write by hand in C. It is obviously not faster than what people write in assembly, but that's a different business, right? So then you are competing with your it's a compiler versus handwritten assembly debate, and we can get into that at some point. But against handwritten C code, verified code from HackleStar is actually as fast, if not faster. It's also, HackleStar code is right now in Firefox. So if you're using Firefox, you're using our code to connect to things like Google. So that's pretty exciting for us, and that's what we do. All right, and it's also the crypto library for Project Everest, or MeTLS, and I'm going to talk about that for a few seconds before I get tired and I say that we're done for the day. Okay. So HackleStar is a verified crypto library. It's a good basis for building a software stack, but in the end, what we care about are protocols. I mean, at least what I care about are protocols, like TLS. How do I build a verified implementation of TLS? Well, in fact, the exact same things that I showed you on how to verify things about Poly 1, 3, or 5, you can build them up to prove things about state machines, about packet parsing. It's exactly the same methodology that works for verifying all aspects of protocol design. And so that's what we use. We actually used it to build this implementation called MeTLS. It's a verified implementation of TLS 1.0 to 1.2 with 1.3 ongoing. And we have a crypto specification of the whole stack, which we then support with a functional correctness, memory safety proof of the entire code base as well. And it's a joint collaboration between my team and Microsoft Research and a bunch of people. It's a large team. And it's on metls.org. You can even try it out if you like. Now, when you expand out from crypto to the entire protocol, of course, there's a lot of things to take care of. So that is the modular structure of MeTLS, or at least used to be. Maybe right now it's even more complicated. And it's got a bunch of modules, about 40 modules of code. It's about a few thousand lines, but 40 modules of code. And each of them is doing something a little bit different. Some of them are doing packet parsing, some of them are doing state machines, some of them are doing crypto. And the things that are labeled with numbers there are actually places where crypto assumptions need to be applied. Okay? So those are crypto primitives about which we need certain assumptions in order for the whole proof to work together. So at the end of it, what you want to prove is that the whole source code of MeTLS satisfies a secure channel definition in the same sense as the crypto model of the TLS would, but you want to prove it about the source code. In order to do so, what we end up doing is saying, let's apply individual crypto assumptions in a game hopping style to individual modules. So for each module, we apply an assumption and we replace the concrete module with an idealized module, which is an ideal implementation of that particular primitive. And after applying a sequence of those games, we obtain an ideal version of the stack, which is the one after all those assumptions have been applied. And we prove by type checking in F-star that this stack that we have at the end, which is your final game, is unconditionally secure, as in it guarantees all the security properties that you want. So this is almost like the crypto verif proof I showed you earlier, but this is working on real source code. It's not a large piece of code, and it is really using the type checking, which is the verification method, the software verification method, on effectively the last game. The last game, which is this massive, still a massive game, where all the crypto bits have been replaced by idealized crypto bits, but you still have to prove that the code around the crypto is not somehow losing the security. So for example, if you had a skip TLS or a state machine attack, even if all the crypto were perfectly ideal, you would not get the security guarantee at the end. So we are exactly proving that you still get the security guarantee, assuming that all the crypto games have been applied correctly, and so on. In fact, we also use type checking to justify the preconditions for the crypto games. So there's a little bit more use of type checking in the proof. But let's just think of it as first you do the crypto proof for all the modules, apply all the games, and now you have this massive game on which you have to prove something. Yeah?
I don't know if it's a good time for this question. So why don't people use this and instead use a library which literally leaks out secrets if it gets a malformed request?
Right. So you're asking why people don't use MeTLS rather than OpenSSL? Well, the first answer is that this is a research software, and which means that, okay, the first version of MeTLS, the one that actually has been fully verified so far, up to TLS 1.2, it compiles to OCaml, and nobody wants to use an OCaml crypto library. So now we are porting the whole thing over to do TLS 1.3 and also compile to C. And then we are hopeful that people will use it. So the crypto library, once we started going to C, lots of people are interested in using verified crypto in C. That's an easy sell. Verified TLS in C will also be an easy sell. Verified TLS in some other language is not so easy to for people to accept. So that's the only answer I can give you. So the performance of this also will be much better once we go down to C, and that's also an important consideration.
Can you do any sanity checks about the spec itself? If it's unambiguous or ambiguous or...
Right, so that's an interesting question. So there are two kinds of sanity checks. So one is if the natural implementation of the spec, whatever that means, natural implementation, is satisfies the security goals we set out. So we are actually in a way redoing the crypto proof here, so that's kind of a sanity check. Whenever we had to apply a game, we have the preconditions that some things, like some keys have to be abstract, which means they have to be secret and only used in this module and so on. So we are redoing some of the checks of the crypto proof. But when we write an implementation like this, we are already making implementation choices. So if the protocol spec was ambiguous in some place, we don't leave open that ambiguity here. So we have already got to make a choice. There are other methodologies where you could have sort of a little bit more freedom, and then you can ask whether all implementations of this spec are secure. Here we are really proving that one implementation of the spec is secure. It's our chosen implementation, right? So for example, if the state machine is not specified, we have to implement it. So we chose one state machine. So it doesn't really give you that analysis here. And just to sort of summarize, the high-level theorem that you get out of here is that there is a notion called concrete TLS and there's a notion called ideal TLS. And we show that they are computationally indistinguishable. So we start from our MeTLS implementation there, which is going to be using our crypto provider, which is Hacklestar Verified Crypto. And it's going to use a bunch of platform libraries for networking and so on. And we write, and there is an idealized MeTLS implementation, which is exactly the same as the regular MeTLS implementation, except that it gets access to idealized crypto rather than the concrete crypto. And we want to prove that these two are indistinguishable. Okay, so that's the goal. And the API that is exposed by both of them is the same. And this is basically going to be a sort of secure channel API. Okay. So how am I doing for time? Is it
15 minutes.
15? Okay. Just one more note. If you actually wanted to do proofs, crypto proofs, like encrypt then MAC type proofs, but you wanted to do them for code that is written in F star, you can apply this methodology that we're doing in MeTLS to also prove things about crypto protocols. So there's an aspect of it which is about crypto proofs. I probably will not get into it, but the slides have a way, they show you how you apply the sequence of games, in particular, how you can use the exact same encrypt and MAC scheme that we looked at in CryptoVerif, and how it looks like when you apply it to code which has been written in F star. Okay. In particular, there is a way of expressing the in CPA assumption on encryption as an F star interface, the UFCM assumption again as an F star interface, and then to compose them together to get authenticated encryption, and then use that within, say, an RPC protocol, and how you can build more and more complex things by using type checking and making sure that you're not messing up the crypto guarantees by actually composing them correctly. but I'm probably not going to go there. Ignore. There's lots of fun stuff. Okay, but at the end, what you want to end, let's just spend a few minutes on the TLS API. So okay, you have this big piece of code, you're applying all these games, and then you're just saying that you verify this code. What are you verifying? Right? What is the thing that you get at the end of it? If for TLS and protocols like TLS, in fact, stating the top level theorem itself turns out to be quite a complex affair, right? So, for example, we saw a little bit of stuff like about ACCE earlier this week. ACCE is a definition that had to be developed just to give a definition for what security for TLS 1.2 means. And it's a fairly complex definition, right? And SACCE is a variant of it, is also fairly complex. So even if you're writing just paper proofs, to give a definition of security is quite hard. When we're talking about a definition of security for a big stack of code like this, it's also kind of quite delicate because you want to give a theorem which is kind of comprehensible to the user, but at the same time an API which the user can actually use. So I'm not sure we have found the right sort of balance for this, but this is kind of what our top level API looks like. So for TLS, you have a type called connection, which is a connection which for each connection that you're going to make. And the way you're going to use the TLS API is you're going to call connect. The client is going to call connect. The server is going to call accept. When you call connect, you're going to give a TCP stream and some parameters that you're going to use for the handshake. And you're going to get back a client connection, client-side connection. The server is going to call accept and it's going to get a server-side connection. Okay? And now they can start writing and reading on this connection object that they have. Also, whenever they want, they can do a re-handshake on the connection, a request on the connection, or a shutdown on the connection. Okay, so these are like different kinds of handshakes that you can do. You can do a PSK-based re-handshake, a key update, whatever. But those are connection-to-connection functions. The main two functions that you want to do is writing and reading. So if you have a connection, you have some data that you want to write, you can write the data on the connection, and you get back a I/O result. And this is a very socket-style API, but because this is what you have to implement if you actually are going to have a TLS library. So the output you get back is I wrote all of your data. So here's a write. I get a write complete, which means I wrote all your data. Or you get to say, or TLS might tell you, I only wrote part of the data. Here's the rest. You can send it back to me if you want. Or it can say, I could not write any data because you in fact have data that you have to read. You must read. Okay. Conversely, you can read data from a connection. You get back a I/O result I, which says, okay, here's a data that I have read. Here you can have it. Or you can say, oh, this is during a handshake, and there is a certificate that has arrived, and I want you to check whether the certificate is good. It's a cert query. This is what TLS libraries do with browsers. It can say, oh, I'm in a handshake, so I'm just going to continue doing the handshake, please. It's going to say, oh, I got a close, or I got a warning, or I got a fatal alert. So these are all the conditions that can happen. Okay. So this is the minimal set of things that you have to support for an application over TLS. So this is you can't get away with. So you have to express your security guarantees on top of this. So the security guarantees that we express here, let's forget that, are twofold. The first thing we say is that when I, the data that I'm going to send, which is this message O, and the data that I get back, which is this message I, are abstract types. They're abstract types indexed by the connection, which means that this is a piece of data that I cannot look at, the TLS library cannot look at. It has to simply take it and pass it over to the application. The only people who are able to open up this data are either the application or deep down the encryption function. The encryption-decryption primitive is the only thing that looks at the raw bytes, or the application is the only thing that looks at the raw bytes. Anywhere in between, you're not allowed to look at it because it's an abstract type. It's completely hidden from you. Also, the index there, which says that it is indexed by the connection, basically says that if I take data from one connection, I'm not allowed to put it on another connection. They are disjoint. They have to be independent random streams. I have to treat them completely independently. So that's the secrecy and kind of the authentication integrity guarantee that data on one connection has to stay on that connection. It cannot be taken outside. And the fact that you cannot open it up and look at it. You have to pass it along all the way to the application. So anytime somebody opens up this data package, it's kind of a declassification operation. So of course your application might be completely messed up and it might take your data, open it up, and put it on the network, right? You cannot help that because the application can do what it wants. It's like the adversary. But as the TLS library, you're promising that you will never look inside the data. And similarly, you can express over this API a bunch of authentication guarantees for the server, integrity guarantees, secrecy guarantees, by adding more and more invariants and preconditions and postconditions to this stuff. But it very soon gets pretty much unreadable, so I've not added them in this API. But you can add as many guarantees as you want, but on top of this API. And what you want to prove is that the TLS library preserves this API as long as the underlying crypto is correct or secure. So that was what we were proving. So let's stop here, and I'll just give some final thoughts. In the end, what we are most interested in, my team and a lot of people who are interested in, is not that a protocol, a construction is secure, maybe that's interesting. Protocol is secure, a bit more interesting. But what we really care about is that the deployed protocol, which is on the internet, is secure. So there is a long distance to go all the way there, but I think with the sequence of tools that we've shown today and other tools like these, which people are using, you can take your guarantees all the way down to the protocol and the software that people are actually using and deploying. But in order to do that, you need to verify all of these steps. I believe that formal security proofs for whatever real-world crypto protocols is now feasible. TLS 1.3 was a good example of this. Many people did proofs of it using tools, using manual proofs, and so on for the real protocol. And I think there are similar results for Signal now as well. And so it's an exciting time to be in this field. There are many tools. I've talked about ProVerif, Cryptographic, and Star, but there's also tools like Tamarind, EasyCrypt, and VST. I would encourage anyone, all of you, to try them out to build your next protocol in those formalisms and do your proofs there, and to build implementations for your constructions in those using those tools. So I'm going to stop there and ask for questions.
Some RFCs have, say, EBNFs or packet structure. Do you think you can conjure a standard for network protocols? Something like an F-star spec?
So right now, we are involved in an effort called HackSpec, which I'm going to present at the CFRG in London, hopefully in next month, which is a formal language in which you can write crypto primitives. So we've written the kind of primitives I've shown you. So I would, of course, like to say that F-star could be the standard, but people don't like that. So they want to write something which looks kind of like Python, but is formal. So we're giving them that. We actually designed a language which looks like Python, but actually has the formal semantics, and you can easily translate it to F-star or to Coq or to EasyCrypt or Cryptol or any of these other languages and do proofs on it. But it's a language which we believe spec authors can write very easily and developers can read very easily, and actually runs. So you can write the specs, you can just run it, and it will pass the test vectors. So for crypto primitives, I think, yes, we can specify a formal language that specifications and RFC should use. It's very close to what they're already using, but better. For protocols, it gets messier because people have very strong opinions about what the right syntax of writing things is. Even packet formats, people will not agree on what actually it should be. So people have very strong opinions about not just the syntax of packet formats, but actually how the packet formats should be themselves. Should they all be TLV sequences? Should they be structs? And there's lots of philosophical debates about that. So I'm hoping that once over time, yes, we should be able to specify protocols also in this way. My dream is to have a format for writing protocols and games and assumptions in a format which is maybe similar to Cryptographic, but maybe something other people can read, from which you can compile things that people are putting in papers, exactly the kinds of oracles that people are writing in papers, with syntax checks, with type checks, and so on. So it actually helps us write our papers as well as helps people who are writing RFCs specify things properly. But I think we're a bit far from that.
Your TLS library, is it guaranteed to be secure only when it talks to another MITLS instance, or is there something I mean, you prove that your TLS library is secure when it talks to another MITLS implementation.
So the easiest way to interpret that guarantee is that you get guarantees between MTLS connections. If you're talking to somebody else, then you still need to make an assumption that they are behaving in the way you think they will be behaving.
Yeah, of course, if the other library has Heartbleed, then you will not.
That's right. So the other library has Heartbleed, then we have no guarantees, right? So, yeah. Well, thank you so much for your patience. I guess we can call it a day.